We're going to continue now looking at the regulation of blood pressure. The body's blood pressure is a measure of the pressures within the cardiovascular system during the pumping cycle of the heart. And we saw in the last part of chapter 18b that it is influenced by a vast number of variables, and it can alter in either direction for various reasons. So increases or decreases in blood pressure is what that means. And everyone's blood pressure is slightly different, and it can change throughout the day depending on different activities. And what we'll see is that those vast number of variables, things like cardiac output, which is controlled or regulated by changes in stroke volume and heart rate, mean arterial pressure, that changes in those factors can be affected by either neural, hormonal, or renal controls. Both neural and hormonal controls are examples of short-term regulation, and short-term regulation of blood pressure is controlled by the autonomic nervous system, to which both the hypothalamus is the boss. And long-term regulation of blood pressure is really controlled by several physiological mechanisms that regulate blood pressure in the long term, but first and foremost, it's the renin-angiotensin-aldosterone system, or RAAS system, which essentially is renal controls, because we know renin is released from the kidneys. What we can see here are major factors that increase mean arterial pressure, and if you increase mean arterial pressure, then you increase blood pressure. So anything that leads to the increase in mean arterial pressure is an increase in blood pressure. You can actually kind of think, at least for the arterial system, of MAP or MAP as the same thing as blood pressure. And the equation for mean arterial pressure was cardiac output times resistance. So it's essentially the amount of blood that enters circulation multiplied by the resistance that blood flow encounters. So we have to take into account things that can increase cardiac output and increase peripheral resistance. So increases in stroke volume and heart rate can increase cardiac output, and the things that affect resistance were the things discussed earlier in 18b, which are the diameter of blood vessels, blood viscosity, and blood vessel length. And blood viscosity and blood vessel length stay relatively the same, so we're going to see that the diameter of blood vessels plays the biggest role in changing or altering peripheral resistance. And a decrease in the diameter of blood vessels actually increases total peripheral resistance because it'll introduce more turbulent flow and decrease laminar flow. And increases in total peripheral resistance and cardiac output will increase mean arterial pressure. So there are two main neural mechanisms that control peripheral resistance. One is mean arterial pressure is maintained by altering blood vessel diameter, which we just saw in that last slide in that chart. And altering blood vessel diameter alters resistance. And resistance is a part of calculating mean arterial pressure, so that can definitely alter mean arterial pressure. Here's an example. If blood volume drops, all vessels constrict except those to the heart and brain, because we want to make sure that enough blood flow is going to the heart and brain, therefore we want to maintain pressure. We also see that we can alter blood distribution to organs in response to specific demands. For example, if your body is in kind of fight or flight mode, we're going to be sending more blood to your skeletal muscle than necessarily to your digestive organs. The neural controls are going to operate via what's called a reflex arc. And this reflex arc is going to involve the following parts: the cardiovascular centers of the medulla oblongata, such as the cardioexcitatory center, the cardioinhibitory center, and the vasomotor center. Baroreceptors, which are pressure receptors, which is a type of mechanoreceptor. Chemoreceptors, which pick up on chemical changes, so solute changes in blood or interstitial tissue, and then even higher brain centers, such as that of the hypothalamus. So the role of the cardiovascular centers are kind of twofold. They're going to affect both the heart and the blood vessels. The cardiac centers are going to affect the heart. The vasomotor centers are going to affect the blood vessels. So vaso-like vessel movement, which we've seen that term before. The cardiovascular centers are composed of clusters of sympathetic neurons located in the medulla oblongata. The two cardiac centers are the cardioinhibitory and cardioexcitatory center. The cardioinhibitory center is associated with parasympathetic nervous system fibers of the autonomic nervous system, whereas the cardioacceleratory center is associated with sympathetic nervous system fibers, again of the autonomic nervous system. The vasomotor center is again also in the medulla oblongata, and it's generally going to be sending impulses via the sympathetic nervous system, and these efferent or signals that leave or go towards effector signals are going to travel via vasomotor fibers. So these are essentially neuron axons of the sympathetic nervous system that are going to blood vessels. That's what we're calling vasomotor fibers. And these vasomotor efferents can cause continuous or kind of moderate constriction in blood vessels called vasomotor tone. So generally blood vessels are under a certain amount of sympathetic tone called vasomotor tone that keeps them slightly constricted. We're going to see that these cardiovascular centers are able to receive inputs from our pressure receptors, our chemical receptors, and higher brain centers. The baroreceptor reflexes are located in the carotid sinuses, your aortic arch, and the walls of large arteries of the neck and thorax. And what they would do is if mean arterial pressure is high, so if blood pressure is high, that increased blood pressure is going to be able to stimulate these stretch receptors, these pressure receptors, and that would send a signal to the vasomotor center in the medulla oblongata. Now, if there is high blood pressure, high enough blood pressure that puts pressure on the baroreceptors, thereby sending a signal to the brain to tell the brain, hey, blood pressure is high, we're going to see that action inhibits vasomotor and cardioacceleratory centers. So we're going to inhibit that sympathetic activity and instead stimulate the cardioinhibitory centers, which will result in decreased blood pressure, because the cardioinhibitory center is essentially the brakes of the heart, and it's going to slow down heart rate. And if you slow down heart rate, you're going to decrease cardiac output. And if you can decrease cardiac output, you're going to decrease mean arterial pressure. A resulting decrease in blood pressure would be to two mechanisms, and I just talked about the one that decreases heart rate, but we haven't looked really at what blood vessels do, and that would be that they vasodilate. So not only would we decrease sympathetic signals going to the heart and turn on the parasympathetic signals going to the heart in order to achieve our decrease in blood pressure, but the inhibition of the vasomotor center would cause basically reflexive vasodilation, or we'd get decreased output from the vasomotor center causing dilation, and that vasodilation includes arterioles and veins. Arteriolar vasodilation would reduce peripheral resistance, causing mean arterial pressure to fall, whereas venodilation would shift blood to venous reservoirs, and it would decrease venous return or end diastolic volume and thereby cardiac output. So we're doubly decreasing cardiac output, and we're immediately decreasing blood pressure, and it would basically be more to follow due to the venodilation that would decrease cardiac output. And so essentially this decreased cardiac output caused by venodilation and by a decrease in heart rate will lead to that decrease in mean arterial pressure. All right, so before I continue, I just want to kind of summarize what we just talked about, because if you don't understand the terminology, it does sound a little bit like mumbo jumbo. I promise you it makes sense, but you do have to take it slowly. So essentially what we're saying is if you have high blood pressure, that pressure pushes on these receptors that pick up on pressure. So if the baroreceptors are stimulated because they're being pushed on by that high pressure, they send a signal to the brain, specifically the medulla oblongata, to say, hey, we have high blood pressure. So what the brain does, what those cardiovascular areas in the medulla oblongata do, is kind of shift things around to bring that pressure down. So we're going to turn off signals going to blood vessels from the vasomotor center. We're going to inhibit the cardioacceleratory center, and we're going to turn on or start sending signals via the cardioinhibitory center. That not only is going to result in vasodilation of arteries and veins, it's also going to result in lowering the heart rate. And lowering the heart rate and causing vasodilation will ultimately decrease cardiac output. Cardiac output times resistance equals mean arterial pressure. So both of those things are directly related to mean arterial pressure. So if we can increase or decrease one, mean arterial pressure. So because of a decrease in heart rate and venodilation, which was able to decrease EDV or venous return, we're going to see that mean arterial pressure is also decreased. So because all these factors are related to each other, if we're able to decrease some of them, the ones that are directly related will decrease what we're trying to decrease, which is mean arterial pressure. And if mean arterial pressure is low, we would see the opposite of what we just talked about. So if pressure is low, then reflex vasoconstriction would be initiated, and that would increase cardiac output and blood pressure. So an example there would be that mean arterial pressure or blood pressure is low, meaning that the baroreceptors are not going to be picking up on stretch, and that lack of stretch will be communicated to the brain. And the brain will say, okay, well, let's inhibit the cardioinhibitory center, turn on the cardioacceleratory center, and let's make sure that signals are going to the blood vessels via the vasomotor center. So we're going to get vasoconstriction and increased heart rate, which will increase cardiac output and increase mean arterial pressure, or basically kind of reverse our initial stimulus. The carotid sinus reflex are baroreceptors that monitor blood pressure to ensure enough blood to the brain, and the aortic reflex maintains blood pressure in the systemic circuit. So there are different baroreceptors for kind of different parts of monitoring blood pressure. And we know that baroreceptors do eventually become ineffective if someone has altered blood pressure that persists, that is sustained. So essentially we're talking about short-term regulation not being enough if someone is experiencing, for example, hypertension or prolonged high blood pressure. And that's just because baroreceptors become adapted to this new high blood pressure or the hypertension. So eventually they'll stop being triggered by the elevated blood pressure levels because they've just persisted for too long. So here, figure 18.11 is going through the baroreceptor reflexes that essentially are helping maintain blood pressure homeostasis. I do highly recommend this figure. I would look at it because it's showing you an imbalance that both begins essentially with a decrease in blood pressure and an increase in blood pressure. So it's showing you kind of both sides of the coin and how mean arterial pressure is changed and how the cardiovascular centers in the brain respond and cause the effectors, the heart or blood vessels, to do something. So before we move on, I just kind of want to establish what are our players here. What's going on? So we have homeostasis of blood pressure in a normal range. That's where we're at with homeostasis. Basically, if there's no increase or decrease, we're just assuming that your blood pressure is within a normal range. You're homeostatic. On the left, we're seeing an imbalance caused by an increase in blood pressure. On the right, we're seeing an imbalance caused by a decrease in blood pressure, and we're going to see what happens because of that. Our main players are baroreceptors. Those are our pressure receptors. They respond to stretch and the lack of stretch in blood vessels because of pressure. We also have to remember these signals from the baroreceptors are going to go to the brain. They're going to go to the cardiovascular centers in the medulla oblongata. Now, what's in the medulla oblongata that's important? Well, it's the cardioacceleratory, cardioinhibitory, and vasomotor centers. The cardioacceleratory and inhibitory centers are going to communicate to the heart information, whereas the vasomotor center is going to communicate to blood vessels. Now, in general, we have a little bit of sympathetic stimuli going to blood vessels. So we have sympathetic tone going to blood vessels. So they're going to be slightly constricted in general. So that's why their responses will generally either be more constriction or turning off the sympathetic nervous system, turning off the vasomotor center, causing dilation. Now, the heart and our blood vessels, these are our effectors. They're going to be the organs that do something. And what the heart can do is we can increase heart rate or we can increase contraction force. Those are the two things we can do. So we can cause muscle to contract more or we can increase heart rate. What we can do with blood vessels is essentially cause muscle contraction. We're not going to be able to increase or decrease heart rate in blood vessels because that's just not the function of that structure. That only occurs in the heart. So our two options when we're talking about the organs, the heart and blood vessels, are increase or decrease heart rate and increase or decrease contraction force. Those are the only two things that occur. And of course, the increase and decrease heart rate only applies to the heart. Now, essentially, what's going to happen is by changing heart rate or contraction force, we're going to change cardiac output and peripheral resistance. And if you can change those two things, you can change mean arterial pressure, which is what we generally measure for the general blood pressure reading. So those are our players. And if you're thinking that's so complicated, I'll say it even more simpler. Our pressure receptors, called baroreceptors, talk to the brain. We turn on and off things in the brain, and that will send signals to the heart or blood vessels, and increasing or decreasing heart rate or increasing or decreasing contraction will change cardiac output or peripheral resistance, and changing those things will affect blood pressure. So that's as simple as I can make it, because you do need to know those terms at the end. Heart rate, contraction force, cardiac output, peripheral resistance. Those terms are all important. All right, so now that we've kind of 3 times over looked at the players in kind of complicated and simpler terms, let's just work through this figure. So again, this is figure 18.11. We're looking at the baroreceptor reflexes that help maintain blood pressure, homeostasis, and this is a short-term regulation process for regulating blood pressure. So over here on the left, our initial stimulus is an increase in blood pressure. So we have arterial blood pressure rises, and that's going to cause stretch in blood vessels, especially those that contain baroreceptors, such as those in the carotid sinuses. That stretch stimulates the baroreceptors to send impulses or signals to the cardioinhibitory, acceleratory, and vasomotor centers. That information will be examined and will have a response. In the case of stretch signals from the baroreceptors, those stretch signals are going to cause stimulation of the cardioinhibitory center, inhibition of the cardioacceleratory center, and inhibition of the vasomotor center. So essentially, we're turning off the 2 centers that use sympathetic nervous system control to increase stuff, and we're only signaling the cardioinhibitory center because it's going to decrease stuff. So it's going to decrease vasomotor impulses that are allowing vasoconstriction or sympathetic tone. So if we decrease the contraction amount of the smooth muscle in the blood vessel, it's going to dilate, and that will decrease peripheral resistance. If we decrease heart rate and decrease the contraction force of the heart, we can decrease cardiac output. And if we can decrease cardiac output, we can decrease pressure, because cardiac output times peripheral resistance gives us mean arterial pressure, or essentially blood pressure. So what we're seeing here is that increased stretch in a blood vessel tells the brain to decrease heart rate and how hard the heart is beating and dilate blood vessels so that we can slow down the amount of blood entering blood vessels and how much resistance that blood is encountering, which will lower blood pressure. And if we look at the opposite, a lack of stretch or decreased blood pressure in the arteries is going to be picked up by the baroreceptors. But the way this is picked up is we'll have a lack of impulse going to the brain from the baroreceptor. So even though it's not a stimulus sent to the brain, the fact that there is a lack of stimulus being sent to the cardiovascular centers does tell the brain some information. This decrease in impulses from the baroreceptors will be able to activate the cardioacceleratory center and activate or stimulate the vasomotor center, but will inhibit the cardioinhibitory center. So essentially what we're doing is we're hitting the gas, and we're going to increase heart rate, increase contraction force of the heart, and also we're going to cause vasoconstriction or increase that sympathetic tone that's naturally existing in blood vessels. So we see that vasomotor fibers from the vasomotor center are going to stimulate vasoconstriction, which will increase peripheral resistance, increasing heart rate and contraction force, increase cardiac output, and those were signals sent from the cardioacceleratory center, and that will increase cardiac output and peripheral resistance, which we know when those increases are seen together will increase mean arterial pressure. And mean arterial pressure is essentially blood pressure, so we'll return back to kind of a homeostatic balance. All right, next let's look at our chemoreceptor reflexes. And so these are still short-term regulation processes that regulate blood pressure, but we're looking at the neural control or the neural mechanism to this regulation. So in the aortic arch and some large arteries of the neck, there are chemoreceptors. And these chemoreceptors pick up on the amount of carbon dioxide, the amount of hydrogen ions, and oxygen molecules in the blood. So here where it says a drop in pH, that would be the blood becoming acidic. So we'd see an increase there in the amount of hydrogen ions. You need to go back and look at pH. I would go back to chapter 2 in your lecture textbook. So anything that causes increased blood pressure would signal the cardioacceleratory center and the vasomotor centers and the cardioinhibitory center. And they would respond as we saw with the baroreceptors. We have a slightly different mechanism here with the chemoreceptor reflexes. If we have large increases in carbon dioxide levels, or the blood's becoming acidic, or we have increases in the amount of oxygen present, then we would see that the cardioacceleratory center would send signals to the heart to increase heart rate and contractile force and increase cardiac output. And the vasomotor centers would increase vasoconstriction, so they would send signals also to blood vessels. And we know that if peripheral resistance and cardiac output increase, then mean arterial pressure would increase. So what that means is that increases in those levels of molecules and ions would cause increases in blood pressure. And we also have influence of higher brain centers. Reflexes that regulate blood pressure are found in the medulla. We know that. That's where our cardiovascular centers are. But we haven't talked about the fact that the medulla oblongata and its autonomic nervous system centers, which are what the cardiovascular centers are, communicates with the hypothalamus, which is the boss of the autonomic nervous system and essentially the boss of the endocrine system. So the hypothalamus and the cerebral cortex, because the cerebral cortex talks to the hypothalamus, can modify arterial pressure via relays to the medulla. So essentially these higher brain centers can take over to an extent and communicate with the cardiovascular centers of the medulla oblongata to change blood pressures. And this occurs commonly when someone's under stress, we see increases in blood pressure, or if someone's trying to meditate, we can see decreases in blood pressure. But the hypothalamus essentially mediates redistribution of blood flow during exercise and changes in body temperature. All right, moving forward, we're going to look at short-term mechanisms that are hormonal. As we were looking at were our neural mechanisms and the higher brain center, so it was twofold. And hormones we know regulate blood pressure. We've talked about ones like aldosterone, and that increases blood volumes and blood pressure. But hormones generally regulate blood pressure in short term via changes in peripheral resistance, or long-term changes via changes in blood volume. So blood volume and changes in peripheral resistance are going to be the mechanism for hormonal controls of blood pressure. So let's just acknowledge some hormones that can modify blood pressure. They would be the adrenal medulla hormones, epinephrine and norepinephrine, from the adrenal gland, and they would increase cardiac output and vasoconstriction. Angiotensin 2 stimulates vasoconstriction. ADH is going to cause vasoconstriction as well, but only when produced at high levels. And then something that opposes or doesn't cause increased blood pressure or vasoconstriction would be atrial natriuretic peptide. Atrial natriuretic peptide is an antagonistic hormone to aldosterone, and so it's going to do the opposite of aldosterone. So it ends up decreasing blood volume, which decreases blood pressure, and that's going to cause kind of a drop in the amount of pressure being exerted on blood vessels. ANP, or atrial natriuretic peptide, is released from the heart. This is a helpful table. I would go through it. Just make sure it's making sense to you, because it should at this point. You should understand the definitions: cardiac output, how heart rate is going to change cardiac output or why that's even having an impact. You should know what peripheral resistance is and how it's increased because of vasoconstriction. Definitely go back and review aldosterone versus atrial natriuretic peptide and how adding stuff to blood increases blood volume, and usually twofold, because not only are we going to be reabsorbing sodium when aldosterone is active, but water follows sodium, and vice versa for atrial natriuretic peptide and how that could affect blood pressure. So you just want to review these hormones, be familiar with them, make sure that their effect, now that you know more about the cardiovascular system, makes even more sense now, and not that you're staying kind of on that topical level of understanding. All right, next we're going to look at the long-term mechanisms for renal regulation. And the long-term mechanisms are renal regulation because the kidneys release renin. And renin release is what is essentially going to cause the production of aldosterone. And aldosterone is going to be our main player, but its production is only achieved via the indirect renal mechanism, which is the ROS or renin-angiotensin-aldosterone system. There is also a direct renal mechanism, and it's pretty simple, so we'll talk about that one first. But these long-term mechanisms control blood pressure by altering blood volume via the kidneys. So we reviewed the hormones quickly as kind of short-term control. I kept mentioning aldosterone. It can be a short-term control, but when it's produced via this indirect renal mechanism, it's usually for long-term mechanism control of blood pressure. All right, so the direct renal mechanism alters blood volume independently of hormones. So that's why it's direct. We don't need hormones. We don't have to wait for them to travel in the blood or bind to their target tissues. So essentially, increased blood pressure or blood volume causes the elimination of more urine, and that reduces blood pressure. So in the kidney tubules, if you have increased blood pressure or blood volume, we're going to generate more urine from basically the ions in the water that have ended up in your blood. They'll be filtered out, put in the kidney tubules, which eventually produce what's called urine. When that urine leaves, that reduces blood pressure because there's not as much volume in the blood, because those things that were causing increased blood volume, therefore pressure, are gone. With decreased blood pressure or blood volume, that would cause the kidneys to conserve water. So they would hold on to water, sometimes hold on to excess ions, and that stuff would stay in the blood. Therefore, we would maintain or even increase blood volume, and that would cause blood pressure to rise. So that's the direct mechanism. It has nothing to do with hormones. Essentially, in response to changes in arterial pressure, we see changes in filtration by the kidneys. We either increase or decrease urine formation, and that will increase or decrease blood volume, which changes mean arterial pressure. The indirect mechanism is the renin-angiotensin-aldosterone mechanism. And just to kind of take a step back, make sure we know what we're talking about, this is the indirect renal mechanism for regulating blood pressure. This renal mechanism is a long-term regulation mechanism. So what we're looking at here as an initial stimulus is a decrease in arterial pressure, which inhibits the baroreceptors. So that's essentially decrease in arterial pressure, no stretch on the baroreceptors. The fact that there's no stretch gets communicated to the brain, which tells the cardioexcitatory center to start sending signals to blood vessels and sending signals to the heart. But it also, long-term, tells the kidneys to release renin. And the kidneys are essentially going to release renin because they're responding to that increase in peripheral resistance and cardiac output, which slightly increases mean arterial pressure, especially near blood vessels like that of the kidneys, like the glomerulus. Kidney releasing renin will lead to the production of angiotensin 1, then angiotensin 2 from a precursor angiotensinogen. Angiotensin 1 being converted to angiotensin 2 requires an enzyme called ACE, which is angiotensin converting enzyme. And it's angiotensin 2 that's the main player here. So yes, as a hormone-like substance, angiotensin 2 can cause an increase in blood pressure. But that's kind of a short-term thing. It's not going to be prolonged unless it works via one of these mechanisms, which is acting on the adrenal cortex and telling it to secrete aldosterone, which increases sodium reabsorption by the kidneys. And wherever salt goes, water follows. So water will be reabsorbed by the kidneys, and putting more stuff in the blood increases blood volume, which increases blood pressure. Angiotensin 2 also directly increases ADH release by the posterior pituitary, which tells the kidney tubules to hold on to water, which increases blood volume, increases mean arterial pressure. Angiotensin 2 also talks to the hypothalamus and activates neurons of your thirst center. That means it'll make you thirsty. If you increase your water intake, that increases blood volume, which increases mean arterial pressure. And it also causes vasoconstriction. So it increases peripheral resistance. And if you increase peripheral resistance, you act directly on mean arterial pressure. So the indirect renal mechanism uses hormones that are oftentimes associated with kind of quick jumps in blood pressure, but it uses them in a long-term regulatory method. And the methods of indirect regulation of blood pressure not only includes the renin-angiotensin-aldosterone system. This system relies solely on angiotensin II to utilize essentially the blood pressure increasing components of the endocrine system and the neural system to increase arterial pressure, but it all begins with renin. All right, so the indirect mechanism is the renin-angiotensin-aldosterone mechanism. The stimulus we saw in the last image was decreased arterial blood pressure, and that would lead to the release of renin from the kidneys and ultimately the production of angiotensin II. So this is our key player, angiotensin II. Renin causes the production of angiotensin II. Angiotensin II acts in 4 ways. So I would go back and look at that image and make sure you understand that these are 4 separate ways in which angiotensin II can act in order to increase arterial blood pressure if the original stimulus was a decrease. And that would be via the stimulation of aldosterone, via the production of ADH, causing the activation of the neurons of the thirst center in the hypothalamus, and acting itself as a potent vasoconstrictor, and that would be a direct act against peripheral resistance, and increasing peripheral resistance would increase mean arterial pressure. That's what we were reviewing in that image that had that large chart. So here's the chart. So it's figure 18.12, so I'd go back and review it. Using the kidneys to regulate blood pressure is a long-term mechanism of blood pressure control. The reason the neural controls and short-term hormonal mechanisms of regulating blood pressure are short-term is because baroreceptors get used to increases in high blood pressure. Some of our hormones, when overactive, can actually cause high blood pressure or hypertension. So it's only when the hormones work with the kidneys do we have the long-term renal control of blood pressure. So here's just a summary of blood pressure regulation. So the goal of blood pressure regulation was to keep blood pressure high enough to provide adequate tissue perfusion, but not so high that blood vessels are damaged. So if you lost that goal in learning all that terminology, go back, review the terminology, understand the definitions, practice the definitions, and then I would go to the charts and see if the charts make sense to you. That's how I would study this after reading the information in your textbook. But it is important to take a step back and realize that the whole reason we were trying to regulate blood pressure, we want to make sure that there's enough pressure to make sure that there's enough flow of blood to the tissues that need blood because it contains nutrients like glucose and oxygen, which are used in cellular respiration to create ATP, which helps maintain the rate of metabolism in cells. There are a couple of different organs that really rely on blood flow, such as the brain. For example, if blood pressure to the brain is too low, perfusion is inadequate. Perfusion is actually blood flow to the tissue that functions in exchange. And the person will lose consciousness if their perfusion or tissue perfusion in the brain is too low. If blood pressure to the brain is too high, though, that person could have a stroke. So we do want to make sure that we balance or regulate blood pressure. And so here's figure 18.13, looking at factors that increase mean arterial pressure. To take a step back, mean arterial pressure is defined as cardiac output times peripheral resistance. So essentially, it's the amount of blood that enters the circulation plus the resistance it encounters by hitting blood vessel walls. So the two things that control mean arterial pressure are cardiac output and total peripheral resistance. In chapter 17, we talked more about cardiac output. We defined it. We talked about stroke volume and heart rate and why changes in those would change cardiac output. In the beginning of chapter 18, we looked at the factors that regulate or change peripheral resistance. And the main one was the diameter of blood vessels because it changes on a regular basis. Whereas even though blood viscosity and blood vessel length can influence total peripheral resistance, they are relatively constant after a certain age, and unless someone has a homeostatic imbalance. So this is a good figure to study at the end of reading chapter 18, but it's showing many initial stimuli, physiological responses, and then results to changing these physiological responses as a response to the initial stimuli. And then the ultimate result in this image would be an increase in mean arterial pressure. So some homeostatic imbalances we want to mention are going to be kind of transient elevations in blood pressure that occur as you stand up, change postures, start exercising, become emotional, maybe angry, or even have a fever. We would see that blood pressure just changes based on kind of what's going on in your life. But we also know that age, sex, weight, race, mood, and posture can also change or cause blood pressure to vary. One homeostatic imbalance we want to pay special attention to is hypertension. Hypertension is high blood pressure, but essentially sustained high blood pressure is going to be high blood pressure that's sustained over a period of time, generally at about 140/90 millimeters of mercury or higher. There is a prehypertensive state where you are experiencing elevated, sustained high blood pressure, but you're not yet in that hypertension range or the true hypertension range. Sorry about the train. There may be transient adaptations during fever. So someone may experience the prehypertensive range while they're experiencing a fever or exercising or emotionally upset. But this prehypertensive range should not be persistent. If it is, then you definitely want to see your doctor about trying to prevent hypertension. We do often find that prehypertension is persistent in obese people. Prolonged hypertension is a major cause of heart failure, vascular disease, renal failure, and stroke. So it is definitely a condition that you want to monitor, talk to your doctor about, take medications for if it's prescribed. And hypertension is dangerous because it's making the heart work harder. Essentially, it's going to be increasing afterload, causing the heart to not only expend more energy, but try to compensate. So oftentimes the myocardium of the heart will enlarge, but it doesn't enlarge appropriately. So it's enlarging quickly where we don't have enough support and it's a weak kind of enlargement. It's not the heart becoming stronger. It essentially becomes flabby as it tries to work harder and increases myocardium, but it does so poorly. This would also generally accelerate atherosclerosis. And so hypertension is definitely a condition you want to monitor, especially as you age. Most hypertensive conditions are primary hypertension, about 90%, which means there's no underlying cause. We do know that there's hereditary factors that go into developing hypertension, but also diet, obesity, age, other comorbidities like diabetes mellitus, stress, smoking. Those are going to contribute to the development of hypertension. So there's no cure, but we can control hypertension. Diet, taking antihypertensive drugs, other activities such as increasing exercise. So cardiovascular exercise is very important, but losing weight, stopping smoking, all of those are important to control hypertension. Secondary hypertension is less common. It's essentially hypertension caused by a disorder, maybe an obstructed renal artery or kidney disease or an endocrine disorder such as hyperthyroidism and Cushing syndrome. But secondary hypertension is essentially hypertension caused by a disorder, and you would treat the disorder in order to treat the secondary hypertension. Hypotension is the opposite of hypertension. So hypotension is low blood pressure, so below 90 to 60 millimeters of mercury. Usually really not a concern. It's oftentimes associated with a long life, lack of cardiovascular disease. We oftentimes associate hypotension with a healthy individual, but it is a concern if it causes inadequate blood flow to tissue. So sudden hypotension, extreme drops in low blood pressure, those could be dangerous. Orthostatic hypotension is something most people have experienced if you stand up suddenly and are dizzy for a moment, especially if you were sitting or reclining and that's when you stood up suddenly. You may experience orthostatic hypotension, which is just a temporary low blood pressure. Chronic hypotension may hint at poor nutrition, and warning signs for Addison's disease or hypothyroidism may be that someone is experiencing chronic hypotension. And then acute hypotension, which is an important sign of circulatory shock. Acute means quickly advancing or developing, so acute hypotension is usually a late sign of circulatory shock, but definitely an important sign. Circulatory shock is a condition where blood vessels are inadequately filled with blood, so therefore they can't circulate the blood normally. If they're inadequately filled with blood, they cannot send that blood or oftentimes send that blood to capillary beds to meet tissue needs, so tissues tend to become hypoxic. Different types of circulatory shock. There's hypovolemic shock, which is a result of large-scale blood loss, vascular shock, which results from extreme vasodilation and decreased peripheral resistance, essentially kind of massive vasodilation, loss of that resistance, therefore loss of the pressure that ensures blood flow to tissues. Then cardiogenic shock has to do with your heart. So when your heart is inefficient at pumping, it cannot sustain adequate circulation, generally associated with drops in cardiac output, low EDVs, and it can lead to cardiogenic shock or kind of a lack of blood flow through the body. And that is it for Part B, Chapter 18. Make sure to watch Part C as well.